To evaluate the first limit for a, we know that it is a limit to infinity. So we can use the relative strength of functions. So what we could do then is we can just check to see how these powers relate to each other. And we can see here that this 1/3 power really doesn't compare to the power 2. This power 1 doesn't compare to the power 4 in the denominator. So we can kind of start eliminating the parts of this and say essentially this is going to behave like 2x squared over the square root of 9x to the power 4. Well, this then must be 2x squared over 3x squared. The powers are the same. The ratio of the powers are the powers are the same. So the ratio of the coefficients then determines the limit. Okay, so the limit of this ends up being 2 over 3. And because it's going to infinity, we can use this type of analysis. For b, this one here, when I plug in the limit, I end up with 0 divided by 0. Well, this is a condition where I can use L'Hopital's. So this is one where we could use L'Hopital's. Okay, now, so I'll use L'Hopital's first. So I've got my condition, 0 over 0. Okay, and then, so using L'Hopital's, I'm going to differentiate. So I get the limit as x approaches 0 from the positive side. This is going to be cosine x over 1/2 root x minus x squared times 2x. Oops, so I'm going to need to zoom in here a little bit. When I differentiate the inside function, I get 1 minus 2x. Okay, and this can be simplified. So I get limit as x approaches 0 from the positive side. This ends up being 2 square root x minus x squared cosine x over 1 minus 2x. And as I plug in 0, I'm going to end up being able to evaluate this. This becomes 0 times cosine of x is 1 over 1. So the limit here is 0. Now, this is a little bit messy, so I'm going to show you a different way to do this. So here I applied L'Hopital's. So just so we're clear, once I establish my condition, I'm going to apply L'Hopital's. Okay, so that's what happened here. And then I just simplified that expression after I applied L'Hopital's. Okay, so another option for this problem is we could analyze this slightly differently, and we don't really need to use L'Hopital's. So what I can do is I can try to use some basic identities. One of the identities I want to use here, and I can kind of see I almost have sine x over x. And I know that's going to end up, the limit of that as it approaches 0 is equal to 1. So I want to use that identity, and I'm going to use it in this way. So I'm going to first of all factor this out. So I'm going to factor my square root x out of the denominator, and I'm going to end up with square root 1 minus x. Okay, now I want to generate my sine x over x. So what I'm going to do is I'm going to multiply the top and bottom by root x. And by doing so, I'm going to end up with a limit that looks like this. Limit as x approaches 0 from the positive side. And I'm going to have sine x over x. Okay, when I combine these two, I get that x. Okay, so then the rest of it I still have to keep track of, times, it's going to be square root x over square root 1 minus x. Okay, and I can evaluate those two parts separately. Okay, using limit laws, I can evaluate this. And so the sine x over x becomes 1 when I evaluate that. And it's times, well, that becomes 0 over 1. which is just 0. So I get the exact same result using some algebra. I didn't use L'Hopital's here. I just did a rearrangement to generate an identity sine x over x. And we should check these by graphing, and we can see what happens on the graph.